All right, with this, I wanted to start off with mistakes simply because it starts to get you thinking, okay, where could I lose points on this? And when you think, where can I lose points, typically you understand, oh, this is important. So can somebody tell me one mistake they see in all of this? Yeah. It has p hat where? The null and alternative both say p hat. What should the null and alternative say? P. If you put p hat, automatically, guys, you're going to be down. Okay? That's very important. A hypothesis test is all about what you believe to be true. About the hypothesis. A confidence interval is about your sample. And you have to keep those two clear in your heads. Okay, so the confidence interval is going to be all about p hat. Hypothesis test is all about p. What else? Yeah. P should be, let's see here, I didn't even read it. Not accurate? Yes, P should be not equal for your alternative. Good. Okay, so we've identified the things that are wrong with the hypotheses. Yes. Uh-huh. And that's okay. That's okay. I mean, they didn't really come out and say simple random sample, but I don't think I would have like gone for that. I said random, I'm happy. Uh-huh. So what would my successes and failures have been for this guy? 228. That's going to be my successes. The flip side of that is going to be my failures. But I do need to check something with that 750. What do I need with the 750? Oh my God, you guys are being awesome. That it is less than 10% of all adults living in the U.S. Yeah. I'm like, where? I guess, U.S. Okay? So we have those three assumptions and conditions that we need to check. We need random, we need big enough, and not too big. Okay? Well, P needs to be defined. And so what would P represent? The percent of U.S. adults or the percent of adults in the U.S. that are obese. Very good. What else am I missing? Julia. The model. Good. What should my model be? X goes to normal. Centered. Where would it be centered? Actually, it would be centered at P, this one, the 34. And we're going to talk more about that today. So because that's not in there, I'm glad you noticed that it's not in there. But we'll talk about how those change between confidence intervals and hypothesis tests. Okay, is this right? I don't know. Did you divide that? That's correct? Okay. Does this sound correct? And again, we're going to talk about this today. But your standard deviation here, because we're focusing on the hypothesis, should be using the hypothesis numbers. Don't worry too much about not getting that. All right, that's going to be that was in the video, but that'll be a focus of today. So they got that to be 0.017. I don't know. Let's assume that math is correct. I have no idea. Z-score. How do we calculate a Z-score? Observed minus predicted divided by standard deviation. So had that been the correct number, this would have been the correct setup. With what is already done here, is there anything wrong with this? You don't know yet, right? Could be looking at that. But basically, this and this should match. Always. Okay? And then the conclusion is also wrong. It says there is a 97% chance that the stated percentage is correct for this region. That is not how we interpret the p-value. Okay? That p-value represents the probability of getting a sample as extreme or more than ours. So that's the probability of getting 228 of 750 adults or more obese if the actual average was 34%, or I should say, or less. Okay? And then we would make our decision. So we're going to be focusing on going through the computations for this, and we'll talk about the middle guys here today. Okay? I think right now I don't want you to kind of focus on that too much. Yeah? When I started doing this, if the p is low, the whole must go, all of a sudden people started remembering that. First couple of years teaching statistics, they could never remember. Do you reject when the p is low or when the p is high? If the p is low, the whole must go. No? How many of you are completely offended right now? Good, thank you. I was aiming to offend Gleb. But seriously, if your p-value is lower than your alpha, what does HO represent? The null hypothesis must go. You must reject the null. Do you think you can remember that? Does that help a little bit? That's just grape juice. I'm like, hopefully he has no drugs in his hands. Right, we're good. Okay. All right. So today what we're doing is we're going to go through the entire process for testing a hypothesis. Okay? Hopefully get some extra practice in today. Well, not extra practice, but practice in today. Working through the full run of this stuff. Okay? Because once we do 18 and 19, everything else is going to follow the same interpretations, the same basic steps. Our assumptions and conditions will change a bit. Our formulas will change a bit. Beyond that, everything pretty much is going to be the same. So, hopefully you all watched the video. So I'm not going to give you time to write this down because you should have written this down already. The 4 basic parts to a hypothesis test. Can somebody tell me what they are? Hypothesis, model, mechanics, conclusion. Okay. Some teachers for this actually have their students break down each problem into 4 squares. Hypothesis, model, mechanics, conclusion. As long as you do those, you're always good. For our hypothesis, your null is always going to be, and this here is true not just for the test that we're doing, but for every test. What I'm putting up here is always true. The hypothesis is that the parameter is equal to the hypothesized value. The alternative is going to be the parameter, the same value, but the sign will reflect what the question is asking. If they're asking for just a change or thinking that it might be different, then your inequality sign is going to be not equal to. Otherwise, we're going to look for an increase or decrease or improvement or worse, and all of that is going to be based off of what your context is. Your model. For here, for now, we only have normal, so we will do n. And the first number is your mean, and your second number is your standard deviation. Please make sure you're always using n. I must say, I'm very pleased this year. I haven't seen anybody writing funky muse. I used to have people writing literally an M or literally a U. No matter how much I tried to get them to draw both at the same time, couldn't do it. Okay, so that's very good. Standard deviation is your lowercase sigma, that little funky T thingamajigger. I look at it and I see a T. I don't know what you see. Conditions met or not. Okay, and these guys here can kind of switch. I don't care what order you do them in. It's just you have to have all of these pieces to the model. And for now, the only model that we have, the only test that we have is a 1 proportion Z test. So by now we've done Z intervals, and now we're doing Z tests. So now you're already seeing we've got another word added to that. The mechanics, those are always going to be specific to whatever test that we're doing. And the mechanics for this test, big one here, because this is part of this. The standard deviation, notice that says SD and not SE, not the standard error. The hypothesis test. I can't repeat this enough. Everybody listening to me? Hugely important. Hypothesis test. Every time you need to put something into a formula, you're going to use that null hypothesis value. So that's what P sub 0 stands for. The null hypothesis value. The null hypothesis value for Q. N. The only place your sample plays anywhere in a hypothesis test is just for that one p hat in your z star, in your z score. So you have to show your calculation for, I usually do the standard deviation first, and then I do the z score, and then I make a statement that either says the probability that z is, but honestly the easier way to do it is the probability that is, and then you just grab your alternative and chuck it in there. Because those two should always match. And then to finish it off, it's just going to be an idea about talking about the normal curve. So we're going to use normal CDF to finish it. And then your conclusion, always, always, always based off of this statement here. And I've even tried to color code it a little bit for you guys so you can see if it is less than, we fail to reject, we don't have. If it is greater than, less than, reject, we have enough evidence. Greater than, we fail to reject, we don't have enough evidence. Always going to be the same thing. With a p-value of, you must state what that p-value is. You must compare it to alpha and state what your alpha is. They're very, very picky here. Typically, the conclusion itself is one whole section of the question. Like a four-part question, that is one of the parts. You have to have all of this stuff. We reject or fail to reject. You literally just say the null hypothesis. Okay? All of this, no context. You just say it straight. Then we either have or don't have enough evidence to support, and then whatever your alternative hypothesis is. Yes? Yep. I mean, if you want to write out what the null hypothesis is, you can. It's just always going to be easier to say this. No. The second part must be in context. And the nice thing with this, through all of the statistics classes that I've ever taken, all of the articles involving statistics or statistical conclusions, they all use that. And they all follow that same idea, where you have to state your p-value, compare it to your alpha, state what that is, because it does change. People use different alphas. And then it is always about whether or not we have enough evidence to go to the alternative. Okay? All right. So, some examples of our alternatives. There are 3 alternatives that you can have. Anybody want to guess what those 3 are? Greater than, less than? Oh my gosh! Hardest question of the day, right? If the answer is not equal to, you have 3 choices: less than, greater than, or not equal to. So we have that one, we have that one, we have that one. All of that is going to be based off of the context of your problem. Now, we take these things and we call them either one-sided or two-sided. Okay? Not equal to. Equal to is like right here, right? Perfectly on point. But we'll accept some wiggle room where we'll be like, okay, we might not be exact, but we'll accept it into here. If it falls on that end over there, or this end over there, then we're saying it's not equal to. That's why we claim that that is a two-sided test. Because there are 2 sides that would say, hey, this doesn't work. Do you understand what I'm talking about there? 2 sides, two-sided test. Could be less than, could be greater than. Both of those work. And when you're doing a two-sided test, basically, we're looking for these red proportions. And you can do that one of 2 different ways. You can find this one, times it by 2. You could find this one, times it by 2. I don't know why. The way I've always done it is I always do 1 minus this one to just get all of the outside. Okay? And you'll see in your textbooks that they talk about that also. But the way I typically do this, and you might want to write this down, if your alternative hypothesis is not equal to, that is two-sided, and that is the calculator command that you'll use. To me, that is the easiest calculator command. Simply because I think it's easier to write negative and positive z than it is to write from negative infinity to z, or from z to positive infinity. So you have this, or you can find one piece and times it by 2. All right, so the not equal to is a two-sided test because it could be less than, it could be greater than. What do you think I'm going to call the greater than? One-sided. OMG. What do you think I'm going to call the less than? Where do these ideas come from? One-sided. Okay, so the not equal to is two-sided. If I have the other ones, those are one-sided because we're only looking at, I'm only concerned if it is over on one side or the other. If I am worried that I think that the rate of high school students who vape has increased, I'm only concerned if we're on that greater than side. I am not concerned if it is on the less than side. Do you understand what that is talking about? I'm only worried about one of those. So when we do a one-sided test, it looks like that. So this could be the lower side. That could be the upper side, depending upon what it is. And sometimes they call it a one-tailed, lower-tailed test because it's less than, upper-tailed is greater than. And depending upon what it is, if you're talking about p is less than some number, that's what this picture is here. We want this area, so I'm going to go from negative infinity, my negative crazy 9s, to whatever my z is. If I was talking about one on this side, I would say that my p starts at z and goes to crazy 9s. Look at this. These things we've done a lot of. Okay? That's the math in this. That's it. It's the interpretations that should be the more challenging bits. Okay, so what we're going to do, give you guys another second to write this down, then we are going to work through an entire hypothesis test, start to finish. Okay, what should you do for every question? Give me a second. So here's our first one that we are going to work through start to finish. This is from your textbook, so it's not in your notes, but that's good because you want as much page room on your paper as possible. So take out some nice clean sheet of paper, or if it already has, I don't know, coffee stains or whatever, that's fine too. Yay, math. And we are literally going to work through each part of this problem. Many of the steps that we're going to take are going to feel exactly like what you did for your confidence intervals. Very, very similar. What was the first thing we did with confidence intervals? Define P. That's what we want to do here. So if we're reading through this, what is P? Percent of or proportion of. Okay, that's using big words. Incidence of abnormalities. I know. I would have just said babies born with abnormalities. Yeah, we'll use incidence. I guess incidence is a shorter word than all of the little words strung out. I don't know, whatever. Just showing you this is not a creative writing class. Do not worry about that. So I'm going to write that down. I'm going to start here with P is the proportion. I'm just going to write prop because I don't like to spell. I kind of stink at it. Let's see. Where is it? Where did you see the incidence? I'm just going to say the proportion of children, because the incidence is in there, but it actually doesn't really apply to the P. It's the proportion of children with birth or either congenital abnormalities. You don't have a Y and now a T's. There we go. Okay, that's my first step. What do you think I'm going to do next? Hypothesis. What would your null hypothesis be here? P is equal to 5%. How am I going to write that? Good, and you need to have that written as a proportion. It's my main part here. P is equal to 0.05. We never do any math with percents. We only do our math with proportions. And so my alternative is going to have that P. It's going to have that 0.05. What is the symbol that's going to go with it? Greater than, because we are concerned with an increase in risk. So that's going to be greater than. This was a little bit different from what we had for our confidence intervals. What was the next thing, though, after we identified P that kind of came in handy with our confidence intervals? Even before that. We defined P and then you listed out all of your bits and pieces. So we're going to do the same thing here. And that's going to be necessary to what we go through. So if I read through this, right off the bat, what is N? 384. And then go ahead and find P hat and Q hat. Okay, so when I go through and I do this, I just list out my P hat and Q hat. N, P, and Q. These are pieces, these are things I'm going to need as I work through the problem. You have to have those listed someplace. Doesn't necessarily matter where, but you do have to have them listed someplace. Now I'm going to do what next? Assumptions and conditions. When we do the assumptions and conditions, and you don't need to write this part down. The assumptions and conditions will use the P of 0.05 and the N of 384. That is it. The assumptions and conditions are things that you should be able to check before you even capture your data, before you have that. Remember, a hypothesis test is 100% about the hypothesis. Okay? So when I check my assumptions and conditions, what's the first one that I need? One more time? Randomization. I don't know. Does it say randomization? No. If we don't have randomization, what do we say? Hope that it is representative. Because without that, I can't take this information and do anything with it. Unfortunately, when we are talking about children, and we're talking about doing a study, we typically look at a general area, and it's not necessarily a random sample. It's just grab all the kids that you had from that area. After hope representative, what's the next thing? Well, even before, okay, we can do large enough. So what's the large enough? NP and NQ. That is not a Q. That was weird. For all of your conditions, you use these numbers. We should check assumptions conditions before we gather our data. Because if we don't meet our assumptions and conditions, why gather data? Stop before you waste. So that means N times P and N times Q. NP and NQ, hypothesis test is about the hypothesis. Do not round. So, are we good? Are we big enough? Yep. Both of those are greater than 10. We have large enough. And there is one more assumption condition. One more time. 10%. Matthew, if you're writing, it's generally easier to stay awake. So pick up a pen or pencil. Okay, how do I check the 10%? Less than. 384 should be less than 10% of what? Of the whole population of children. Not kids with abnormalities, just children. 384 should be less than 10% of all children born. I'm not going to say born because if it's a child, it's been born. Can we agree on that? Philosophical discussion right there. Okay. Are my conditions met? And if the conditions are met, what do I say? Before that, before we talk about the test, what do I do? The model. The model I'm going to use, what kind of a model? Normal. The model, hypothesis test, is about the hypothesis. Where will my model be centered? P, the number from your hypothesis. What will I use for my standard deviation? P, the number from the hypothesis. Okay, this is the biggest thing I need you guys to get. Confidence intervals, all of your math is about your sample. Hypothesis test, all of your formulas, all of that stuff is about the guy in the hypothesis. So that means my standard deviation will be P Q over N. Because I've met my assumptions, I can use this model. And because I'm using that model, what can I do? Name that test. A one proportion Z test. So the big pieces that we've done hypothesis, model, assumptions and conditions, which give me my model. And that's what we've done. And now we're going to do the mechanics. When we're doing the mechanics, for a confidence interval, our mechanics was that the confidence interval was p hat plus or minus z star times the standard error, right? For a z test, our math that we need here is that z is p hat, and this is the only place that p hat comes out, minus your null over your standard deviation. And you can either call that the standard deviation and just tell me what that's equal to. Literally, that's good enough. Because look, I have p hat written here. I have p sub 0 here. I have standard deviation here. So I have all the bits and pieces. Or I can put them in. P hat was 46 out of 384. Q hat, I'm sorry, why am I doing Q hat? I'm doing standard deviation. Minus P over the standard deviation. I don't know what that was. What is that? Square root of 0.05 times 0.95 divided by 384. And I'm just going to do the math for that. I'm going to say 46 out of 384 minus 0.05, enter, divide that by this guy. Okay, did you get that same number that I did? I'll just do 2.8. Z-scores need to be out to 2 decimal places at least. If you want to take it out further, you can. I'm just going to do it to that. Questions on what I've done so far? Then the last bit here, I have done the Z. I need to find my p-value. And to find the p-value, you have a choice. You can either say the probability of getting a sample greater than 0.05. So I've just switched this instead of talking about p. I'm saying a sample bigger than 0.05, or you could say the probability of a z-score greater than 6.28 equals. Let's think about what that means. You can either write one of those statements, or you can draw a picture. If that's 0, 6.28 is all the way over here, and it's that little blippy right there. How do I find that proportion? Normal CDF. So, normal CDF from 6.28. And to get that, I'm going to take this guy up here This key right here, do you see that? STO, the store key. That's actually one of my most favorite keys on the whole calculator. Because if I hit that key, it just says I'm going to store that as X. And what's really nice about that is when I do my normal CDF, I can just type in X. I'm just going to grab that whole thing. I don't need to worry about rounding or anything. And what is my upper number going to be? All of those 9s. 0 and 1 because it's a z-score. And that's what I got for my answer. Do not write that P is 1.75. A proportion has to be between what two numbers? 0 and 1. Can I have a proportion of 1.75? Heck nah. So what you can do is you can say whenever you see that E, anytime, I'm giving you the permission, anytime you see that E, go ahead and just write, that's pretty much 0. Because this, if you think about it, this is going to be a point, and then we're going to move that decimal 10 places, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't know about you, but I'm okay saying that's about 0. You get what I'm talking about? Catch what I'm throwing at you. If they have to write it with an E to a negative, just say you're pretty much 0. I don't care. If you really want to write it out, you're a dork, but okay. Okay? And then I'm actually going to kind of mix up the order that the questions ask me. But did you guys get that all right? So if you see here, hypothesis, model, which includes your assumptions and conditions, mechanics, what comes next? Conclusion. So you guys tell me, how do I write my conclusion? Can you read from a piece of paper or a poster? Can you tell me what I need to write down? Starts with a W. With what? A p-value, and you have to write that word out, p-value, and then you can just say equal to or approximately 0. And then what? And you can even write the symbol. You can even write the symbol. Did I tell you what alpha was here? If I don't tell you alpha, what are you going to use? 0.05, sorry. With a p-value approximately 0 being less than alpha of 0.05, if you want to write that out, like less than, and the word alpha, okay. I embrace the inner lazy person. It's my outer lazy person also. What are we going to do? We reject, and you can even say the null. If the p is low, what happens? That home must go. We reject the null. Then what do I say? We have enough evidence to support or to claim, to support the claim that what? Almost. Come on. context that the proportion of children with congenital abnormalities is greater than 0.05. Literally just pull in that, tack it with that. We have enough evidence to support the claim that the proportion of children with congenital abnormalities is greater than 0.05. How are we doing with that? Would you agree with me that this is a pain in the butt to write down? It's kind of a pain in the tuchus to write. But were any of those steps difficult? A lot of writing, none of it was creative. It's called technical writing. You technically write what I tell you to write. That's it. And you just got to write a lot. And the only thing that we kind of skipped for this is it says explain what the p-value means in context. This is a very common way that an AP or any question will finish it off. They'll say, what does that p-value mean? And what does that p-value mean? It means that there is about a 0% chance of what? What does it say? And we're talking about more extreme than ours, right? So our sample said what? What was our sample? 46 out of 384. More extreme. More extreme is going to go which direction? Greater. There's about a 0% chance of getting more than 46 of 384 children with congenital abnormalities. There we go. What? Through random sampling variability, okay, are we done? Nope, we left something out. Read the statement over there. What does it says? What do I not have? If the null hypothesis was true. If the actual proportion was 0.05. And you can change that order around. You can say there's about a 0% chance of getting a sample of 40, or a proportion of 46 out of 340 if the actual proportion of children with congenital abnormalities was 0.05. Like you can move around where you put that context. It has to be in there. Okay? Have I blown your minds? Or just exhausted your hands? The hand part? Yeah. Well, that right there, I don't even know if I can get it all in one shot. I can't. Let's go. There we go. That right there is typically what a free response and multiple choice don't happen at the same time. A free response AP question will look like. That's generally going to be 1, 2, or 3. Will look like that. Okay? All right, let's keep going. We've done that. We made the conclusion. So I want you guys to read that last little question. Quickly. Lots of different. Okay, well, there's one main answer, yes or no, but then a lot of different justifications. What do you think? Eden, you're shaking your head no. Why? Correlation is not causation. Careful. Correlation isn't a word we use right now. That's different. What was it that we did? Even before that, how did I get my data? Did I do an experiment? I did a study. What's true about studies? You can't show cause and effect. You can talk about an association, but what do you need in order to show cause and effect? An experiment? Why? What does an experiment do that allows me to talk about cause and effect? Test, control. It has control. You are manipulating something. Nobody is going to allow me to manipulate the way children are born to figure out about birth defects. Imagine the lawsuits that would be following that kind of a study. Also, when we're going through this, the whole idea is we cannot talk about cause and effect. All we can say is whether or not we have evidence that the proportion has changed. My study had nothing to do with environmental chemicals. There are a lot of things that could contribute to that. Maybe it's not environmental. Maybe it strictly has something to do with, I don't know, parents, genetics, the crazy doctor giving birth, or he doesn't give birth, but helping with the birth. Maybe he's like using the wrong tools, which is why you see malpractice suits. Was you or a loved one born with congenital birth defects? So call the law offices of something in Solcombe or whatever. Okay, contain your excitement. No giggles. I don't really go crazy with him. I much prefer my Zachary Levi over there. He's so much cuter, I think. But hey, girl, because you can see this guy going, hey, girl. Your P must be greater than 0.05 because I failed to reject you. Best Valentine's Day card ever. No? You don't think so? Okay. Try this one, start to finish, all on your own. What? I think that you guys would probably be okay with the first part. So P is a proportion of students whose mothers graduated from college. Listing out my bits and pieces. The P they gave me was the 0.31. P hat is the 0.32. Just kind of keep that straight. So your null and alternative should have the P in it. So far, so good with that? And because all it was asking for a change in education level, I don't know. Are you concerned about an increase, a decrease? We're just talking about a change. So that means my alternative is not equal to. We check our assumptions and conditions. Mother's education should be independent. I mean, unless there's something funky going on, your mom's education should not affect your mom's education. Do you understand what I'm talking about there? It's kind of like flipping a coin. One should not affect the next. Okay? You hope the sample was representative. So you could have you should have done, no matter what you need to talk about, hope the sample was representative, because it didn't talk about how that sample was collected. 10%. Does it say random? I don't see it. Where? Oh, randomly chosen. Gotcha. Thank you. We said 10% rule should be less than 10% of all students. And it's not necessarily just that one year, but all students everywhere. Okay? And then when we check our sample size condition, it has to be P and N, Q and N. But no matter what, you get big enough. You have to physically show these numbers. I don't care if you show these calculations or not. But when you do those calculations, you have to be using the hypothesis. Please remember, hypothesis test is all about the hypothesis. So it is that value that should be in almost all of your calculations. Confidence interval, it's about your sample. So that's the value that should be in everything. So I have my sampling distribution. X is approximately normal, centered at 0.31. Your standard deviation ends up being about 0.0051. You know you're going to do a 1 proportion z-test. We get all of that okay. Any questions on what's up there? Because this is the least new. I mean, we did hypothesis tests, we've done assumptions and conditions, we've done models. We're okay with that. What I'm more concerned with is the mechanics. Because your alternative said not equal to. You should have gotten the same z-score, 1.98. We all okay with that? 1.98? And you can think about this because this is a two-tailed test. We're putting together both of these. So you can do it in a couple of different ways. You can say probability that we start at z and go to infinity and times that by 9. You can say negative infinity to a negative z, times it by 9. Did I say times it by 9? Times it by 2. My personal preference, what I do, is I do 1 minus the normal CDF, and I use the negative. And since I stored my answer as x, you can literally do negative x to positive x. Yes? Because this is not actually part of your work. This is never going to count as part of your work. You can show it. But I wrote this down simply because I want you to know where those numbers come from. All you need to write down is you can either write the probability that x is not equal to 1.98, probability that p is not equal to, or p hat is not equal to 0.32. I'm sorry, 0.31, that was my p. Or this guy here. And you should get 0.0479. Can everybody get those numbers? Seriously, a lot of times you're like, oh yeah, I know what she did. But you don't actually type into your calculator, and then you go back to type into your calculator for another problem, and you go, oh, crud. So we're okay? That's my p-value. What would you do? You would what? We would reject the null. And say what? With a p-value of 0.0479 being less than alpha of 0.05 because we weren't given anything else, we reject the null hypothesis. You're welcome to say just null, that's okay. We have enough evidence to support the claim, or to support that the what? Proportion of mothers that graduated from college is not 0.31. Now, this said, the last part it was asking you was to discuss that. Why might I not, say, go out and write a big paper about this? Oh my gosh! The percent of mothers, the kids whose mothers had graduated from college, it's now increased from 31% to 32%. Ah! Why might I not go crazy about that? Because it's what? It's not a big jump. I mean, it's like, yay, you increased. Woo! Students, they increased their AP score. The number of the pass rate. 7. That just might be because I didn't have the exact same number of kids taking it, and that's how the math worked out. Yes, it was statistically significant. There's a difference between statistically significant and what's called practically significant. What do you think I mean by when I say practically significant? Your bag of chips might be statistically significantly more than the average bag of chips, but nobody cares. It's like, yay! Yes, you have met the definition of bigger. Wow, you had one more chip than average. Ah! Nobody cares. Nobody cares. Do you get what I'm talking about? Now, it might be a big deal if I went from 31% to, let's say, 40%. That's a big jump. That's something to go, ooh, about. A 1% change. Yeah, I mean, not much. Okay? All right, this one is in your notes. And we're probably not going to get through it, but let's get through as much of this as we can. I know you guys probably haven't had time to finish this. That's okay. Class is going to finish no matter what. So I do want to go over this really quick just to make sure you understand what the expectations of this are. And by the way, the average AP question is not going to have any of this here. It is simply going to ask that question. So you'll have to know that these pieces are part of it. The explain what the p-value means in this context, that'll be an optional thing, and they'll tell you to do that if they want you to. But the general idea here, your hypothesis test, your null should have been that p was equal to 0.28. The alternative was that it was greater than 0.28. We were told random. We had less than 10% of all Black Americans. N times P, not NP hat, NP was 224.28, and Q was 567.72. Those are both bigger than 10. 576, not 567. Doing a 1 proportion z-test. This doesn't have the distribution listed here, but it should. You should have come up with a z-score of about 6.29. Did you guys get that for your z-score? 6.29. So that's another approximately 0 answer. With a p-value so small, or approximately 0, which is less than alpha, of 0.05, you need to state that. This isn't to AP grading requirements, just so you know. There is evidence to suggest that the proportion of Black Americans who were not able to afford medical care is more than 0.28. So, just so that you guys know, you do have homework next class. Due. Tomorrow night. Not tomorrow night, today's Friday. Sunday night. You do have a quiz next class. Tuesday night, because you don't have, yeah, whatever. We'll get to there sooner or later. And I will check to make sure the due date is set correctly. Thank you, ladies and gentlemen. Have a great long weekend.